Again, nothing too new or anything. Remember, when you're getting ready to graduate, the term before you expect to graduate, that's when you do your application for graduation. And it starts with a review of your degree plan. That's called the degree audit. Probably good to do that with your advisor. So get with your advisor before, and either right before or sometime before they open up the registration for the next term, so you can get all worked out. And then when they do open it up for registration, you can get the courses you need to graduate there. And if you don't see the courses on the schedule, then you can maybe have time to see if you can talk that department or instructor or whoever into offering what you have to graduate. And then you apply to graduate online, and then hopefully everything will be lined up. If you can't get the courses you need, you might try to do a course substitution. So that allows time for that to go through in plenty of time before. All right, number two, they, as far as I know, are still looking for note takers on both campuses. So check with Dr. Renee Herndon on this campus, or Ms. Janine Jones on the Birmingham campus. And then they also were looking for tutors, peer tutors, in the Space Center on both campuses and the Student Support Services here. Space Center on Birmingham was looking especially for math, English, biology, computer science, and Spanish. So certainly y'all, both of you, be great tutors in math. Okay. All right. And I know Clark said he wanted to ask some questions from the book that are similar to test questions. So you got one or two or more there. This is chapter 4 stuff.
Well, see, I don't have any of chapter 4.
Oh.
So I don't know any of the examples.
Okay. What questions did you have?
Well, I had a question.
Okay.
I was trying to find one similar to number 9.
Okay. Let's see. Okay. Is number 9 find the indefinite integral?
Yes.
Integral of sine x over cosine 8x
Yes.
to the 8s ds. Okay, indefinite integrals were 4.3, I believe. Well, that's definite integrals there. So maybe it's 4.2. Well, maybe it was 4.4. Yeah, it would be 4.4. Sorry about that. I got them backwards in my head. This book does them a little bit differently from most. Yeah.
And the main thing that I need is one that has the cosine to the some power.
Yeah. I'm sorry, wait, I may have said it wrong. No, 4.5. I'm sorry. Why was I going there? This is a substitution problem.
Yes, sir.
Remember?
Yes, sir. That's not necessarily what I'm struggling with. What I'm struggling with is I can't remember what to do with the 8.
Okay.
And that prediction is wrong.
Okay. All right. All right. I would say on page 306, something like number 48.
That's 7 pages before I have.
What's that?
That's 7 pages before the first one I have.
Oh, really?
That's why I don't have chapter. I mean, in order to make space in my book, see in the class over the summer we started at chapter
5, yeah.
So that's where I thought we were going to start. So
Okay.
I don't have chapter 4 anymore. So
Oh, okay. What's that?
What was the page number again? I can show it to me. Take a picture of it. Yeah, this one.
Okay, I couldn't quite hear what you said.
What's the page number?
306.
306 and example problem.
48.
Right.
All right. So, I mean, I can write it down once I get the word mark here. Okay. All right. Oh, Jordan, we had some questions from chapter 4 first before we get back on chapter 5, so that's what we're doing right now. So we're on page, second? I'm sorry? Okay, I thought there would be some questions on summation.
I have one on that one too.
Okay, so well then we'll hit that as well. But this was the one I asked first. This is page 306. And this is our 4.5 exercise, number 48. Okay. And that was the integral of sine x over cosine cubed x dx. Okay? Now, what would be your approach on a problem like that?
Say u equal cosine cubed x.
Yeah, why not? Wait. Simpler. Let u equal,
Cosine x.
yes, u equal cosine x. The innermost part of the most complicated looking part. Innermost part is just the cosine function. Then, du is equal to negative sine x dx. Perfect. Except we don't have a negative sine x dx, we have a sine x dx. So we
Divide by -1.
or multiply by -1 and make that minus du and positive sine x, right? Dx. Okay? What's that? Derivative of cosine is negative sine. Is that what you're asking? Yeah. Okay. So, what does our new integral become?
It would be a negative out front.
Negative out front.
And
du on top.
over u cubed.
Q. Okay? Can you think of another way to write that?
Du times u to the -3.
U to the minus 3 du. And I bet you can take it from there. Can't you?
Yeah. I was fouling up earlier without.
What's that?
That's where I was messing up earlier. Is I just kept it.
Yeah. You don't get the eighth in there or whatever in there. Okay. Can everybody go from there? I'll be glad to finish it, but I just figured y'all can do it. Huh?
I don't think it'll kill us if you finish it.
What's that?
I was just saying I don't think it'll kill us if you finish it.
Okay. Well, what would be next? Because I'm going to just ask you what did that write down. Minus, what would that be? U to the, okay, wait. Second? You're doing an antiderivative now. Okay. Now that minus and that minus go out, and you need one other little thing here. Plus c. Now probably the preferred way to write that would be 1 over 2 u squared plus c, but what is u squared? U. What is u? What is u anyway? No. Okay. So that'd be 1 over 2 cosine squared x plus c. Now, no, secant. 1/2 secant squared x plus c. Okay? Both of those answers are perfectly correct. use the minus 2 over 2 is what that would be. Catherine. The bottom part of the alphabet is doing quite well. The top part only has one person here. Okay. All right. Now, was there a question?
I thought that was 12.
Yeah.
How do we go from u to the negative 3 to u to the negative 2?
Okay. How do you do an antiderivative of a power?
Oh yeah.
How do you do it?
Add 1.
Add 1, and 1 plus negative 3 is?
Is negative 2.
Okay. So that answer what?
Yeah, right.
And then you divide by whatever your new exponent is.
So you can put cosine negative 2 over 2.
Okay, yeah, you could write it that way too. Cosine to the negative 2 over 2 plus c. That would be another possible way to do it. At this step, plug in cosine to minus 2x over 2 plus c. That certainly is a way to do it. I don't generally like having negative exponents, so that's why I moved it downstairs. But that is correct. I wouldn't count that wrong. Okay. Any other questions on that one? Did you have another? Yeah, it was a long time ago, wasn't it? Okay. Any one of them, or?
It's just the one that it was squared.
What's that?
It was squared. I know you used the formula that's squared.
Right.
I don't know how to plug it in.
Okay. Are you looking at number 1 then?
Yeah.
Okay. I'm pretty sure that's in 4.2 because we didn't do 4.1. I think this is 4.2.
I know what the formula is.
Okay. That's the n times n minus n plus 1 times 2n plus 1 over 6. Yeah. Okay, except now your n is I minus 8. Right.
N would be 21.
Second?
N would be 21.
I still couldn't quite hear you.
The N would it be 21?
Oh, okay. Yeah, but you got a little something else to do with that first. Let's see if I can find something like it in the... What's that? No, let's do one from the book so anyone can follow what we're doing. Would this be like number 21 at the bottom of page 267? You have that? Oh, okay, never mind. I'll just write it down for you. Okay. You got all this? Can I go to a new one? Okay. Well, you can write it. I'll give you time if you want to. Got it? Okay. So let's erase all this mess, timing stuff, and we'll do page 267, 4.2 exercise. Number, what did we say?
41.
I lost it. 21, there it is. Yeah. All right. Here we have the summation, I equal 1 to 20 of I minus 1 squared. where would you begin? The one on your test. Second? Yeah, exactly. And what would that give you? The summation I equal 1 to 20 of I squared minus 2I. Second? Plus 1. Okay? All right. Good deal. Now, I'm going to take one more step here. You may not need it, but I'm going to take it. I equal 1 to 20 of I squared minus 2 times the summation of I equal 1 to 20 of I plus the summation from I equal 1 to 20 of 1. That last one's really hard. Okay. Right? Yay or nay? Well, there's no guessing involved.
Yeah, this is the summation of its parts.
Yeah, the sum of the summation or the summation of the sum of the sum. Yeah, the summation of the sum of numbers is the sum of the summations of those numbers. Okay, and this one in the middle is a product of a number times the summation of a number times an I is the minus is that number times the summation of I. So just those two rules. That's the theorem 4.2 I think it is that they were saying. That you'll find on page 259. Okay. So let's plug in what those are. Summation of I squared is the one that we were just talking about. That would be your n is 20. So that would be a 20 times a 21 times a 2 times 20 is 40 plus 1. That would be 41. You want me to write that down? Maybe I should do that. Sorry about that. Write down what that is first. Okay. All right. This will be from page 259, theorem 4.2, number 3. That part tells you this is n times n plus 1 times 2n plus 1 over 6. Okay, that's what that is. But your n is 20. Just remember that. Minus 2 times the summation of I, which is n times n plus 1 over 2, where your n is 20. What's that? Yeah, 20. This problem is 20. The one on your test is 21. Okay? And then your plus 1, that's the number 1 there, and that's the C times N, plus C times N, where your C is what the number is, which is 1 in this case, times N is 20, right? So this will be 20 times 21 times 41 over 6 minus 2 times N times N, 20 times 21 over 2 plus 1 times 20 is 20. Okay? Here I can take out the 2's there. Here, 2 will go into 20 10 times, and that would give you 3 here. 3 will go into 21 7 times. So you have 41 times 70. that comes roaring back. Okay. So 70 times 41 would be a 0. This is page 267, 4.2 exercises 21. This is like one on the test. Be a 0, 7, that would be a 7, and this would be a 2870 minus, see if I can read my writing there, 20 times 21, that would be 420, okay, plus 20. So that would be 400. So that would be 2470. I hope is the answer there. Now that answer 21 is in the back of the book, so you could check your thing, and that was 4.2. Four, 4.2, number 21 is 1876. How did they do? No, that's 23. 2470. Yes. Okay. So, yeah. Is that what you needed?
Yeah.
Okay. Were there any others?
Number 4 was a little confusing for me.
Number 4. The graph of F consists of the line segments. Okay. That was a hairy one to type. So I hope I got it typed right. Now what I'm going to do on this one, I'm going to clear all this out. Okay. And then I'm going to draw a graph for you. So I'm probably going to do more of this than I should. But everything here is positive. So I'm going to do my graph here. And we need to go from x equals 0 to 11. So let's do 11 here. And this will be 5 and 6 here. That will be 2 and 3 here, 1 and 4 here. Eight and 9 here. 1, 2, 3, 4, 5, 6, 8, 9. So this would be 7. This would be 10, 11. Okay, that's approximately my x-axis. My y-axis, we'll just do, I'll try, hope that it worked. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't think we'll need that high, but let's do it. Okay, x minus 1 from 0 to 3. How would I plot that? Oh, this is test 1, number 4. How would I plot that? Okay, it sounds like a dentist at work. Never mind. Okay. What we got? That doesn't even seem like a right problem. I may have messed up something here. Let me find my original. That doesn't look like that's even right. This is number 4.
Yes.
Yeah, that's right. Sorry. Okay. So I messed up my drawing. was thinking everything was positive. It's not. So I'm going to have down here -1 and a -2. Yeah, get out of there, get out of there, get out of there. No. Okay. I won't need this many up here. I should have moved everything up. I don't need all these. But we'll do it. Okay? When x equals 0, y is equal to -1. And when x is equal to 3, what is y? +2. Right? So that's the straight line with slope 1 from 0 to 3. X going from 0 to 3, y is going from -1 to 2. You see? And y is equal to 2 from x equal 3 to 4. There that is. You see? So you see how to do this? I mean, it's not that 3 to 4. X equal minus, y is equal minus x plus 6 from 4 to 8. So when x equal 4, what's that? 2. So there we are at 4. We're right where we belong. And when you go to 8, you go down to -2. Okay, so it's down here. So that's aligned with slope of -1. It should cross it at 6 there, because it's 6 minus 6, it would be 0. So, okay. And then x minus 10 from x equal 8 to x equal 11. So that would be a -2 at 8 to +1 at 11, right? So it goes like that. I think my spacing's off, but you get the general idea. Okay. What it says, the graph consists of those segments. Evaluate the definite integral from the integral from 0 to 11 of f of x, and this is your f of x using geometric formulas. Okay? Now, using geometric formulas. Okay? Or you can just do your integration. I don't care which way you do it. Just give me an answer. So what you could do, if you wanted to, you could write down geometric formula. I would do, this is going to be a negative area here, and you know exactly what that is, right? 1/2, -1/2, right? And then if you did this here, this will be from 1 to 2, so that's going to be exactly half of that. Okay, 2 by 2 is?
Oh, no. So it'd be
2. Okay, so this is a -1, 2. So you see, you can go like this. Oh, get out of there. Okay. And then you could do that one, and that's easy to do, right? Yeah. And then you can do this one. That's half of that one. And then you can do, I would break this into 2 pieces here. You could do this one, and then this one. Now this is only going to 9.5 here, so that's, I think, yeah. There goes the dentist again. So there's another, this is 1.5 this way and 2 that way. And then this is 1.5 this way. So that's what they mean by geometric means. Or you could do it this way. The integral from 0 to 3 of whatever that first integral is, x minus 1. plus the integral from 3 to 4 of, get out of here, 2, because y is equal to 2. Yeah, you can do it that way. So you can do it either way you want to. Calculate the area. Remember, anything below the axis is going to be a negative number, above is going to be a positive number. And do each geometric piece like that, and then add them together. Or you can do the individual integrals, just like you read them. From 0 to 3, it's that. From 3 to 4, it's that. From 4 to 6 or 8, or whatever it is. And you can integrate them that way. So you can do it either way you want to. Okay? That give you enough to get going? Any questions? It looks like you have questions, but I don't hear any. None? And let me give you a hint here. Since this is going from 2 this way, 2 this way, this is 2 this way, and 2 that way, this and that add to. Well, this is negative, that's positive. That adds a 0. So that really makes that part easy. Okay. Can't do the same thing here because this is 2 by 1.5 here. Oh, that is 1.5, isn't it? Yeah. So this part here and that part here are add to 0. So actually, this is the easy way to do it because you can just look at that and see those add to 0. I think you'll see that if you integrate that way. But this is a minus, that's a plus, and that's a plus. The rest of them cancel each other out. Don't we? No, they don't. This isn't, I said this wrong. This isn't going from there. This is going from 8 to 10 here. My drawing was better than I thought it was. I thought I was off. This is 8 to 10. There's that answer. That's negative, and this is positive because that's only going to 1 at the end, not to 2. So I was giving you bad information. So that doesn't, this last part doesn't add to 0. This is a bigger negative than that's a positive. Now let's see.
Now looking back at it, isn't it
But,
all cancel each
but
other out?
this negative, isn't that the same as this positive here? It is. So these two add to 0. These two add to 0. So you got,
You're left with 3.
and this one and that one add to 0, right? Okay, so I think what you got left is this right here, isn't it? Boy, that turned out way too easy. I shouldn't have been saying all that I said, should I? Sorry about that. Huh?
It was helpful though.
Okay. Sorry about that. That was too much. Okay, everybody okay with it? I'm sorry, I misstated here. You're not okay with it. Okay. What's wrong?
What was just going to do with the interval from 3 to 4 to 2 years?
Say that again.
The interval from 3 to 4 to 2 years.
Well, if you see that the other parts do what I was indicating they do, yeah, that's okay to do. And that's pretty easy to do. It basically, that one integral, I think.
You just got one number. You take a derivative of it. Is it 1 or 0?
Okay, are you saying take a derivative or an antiderivative?
Something like, no, I was asking for something else.
Okay, I'm sorry. What is
You
it?
just got one number, like a 6. You take a derivative of it.
Why would you take a derivative of it?
I'm just asking.
Yeah. You're wanting to know what the integral of this is. The antiderivative is, how does the questions go? Yeah. The graph of f consists of this. Evaluate the definite integral. That's what you're wanting to evaluate. It says do it geometrically, and if you look at that geometrically, you can see everything basically cancels out except that little piece there. And you can do that geometrically too. This is 2 by 1. Right? convince yourself what I said is true. My drawing stinks, but you know, if you draw it nicely, neatly on graph paper, I think you'll see the thing happening that I'm thinking is happening. Okay. Because they all have slopes of plus or minus 1. That's what makes it really easy. Easy to graph, but also easy to do calculations.
And so, like with those up there, you would just do like 0 minus 1, or actually you do 3 minus 1 minus 0 minus 1, and then just keep on going like that.
I'm not sure. Like this one right here, if you did the integration, okay, what's the antiderivative of x minus 1?
1. Right?
How'd you get that?
This is x.
You do antiderivative of x minus 1 would be x greater than 2 minus x.
Oh yeah, that's right. I was doing the derivative.
I know it. Okay. I think you were doing a derivative. Y'all were confusing me with your derivatives. Okay, these are antiderivatives. Integrating. Okay. What's that? It doesn't ask for one. It asks for the integral, definite integral from 0 to 11 of f of x dx, where this describes f of x. And it said do it geometrically, and I drew it for you geometrically because I knew that was hard to read, but I probably did way too much. Say that one more time.
The integration of 5 to 6 on 3dx. I'm just saying so.
What? Okay, what are you integrating? I can't hear you.
Well, I was just saying, like, can you do that? Because I'm getting kind of confused. Like, instead of doing the numbers that's already up there, could you work one out with different numbers?
Okay. But what different numbers? Down here or up there or where?
I was just going to give you some numbers.
Okay.
You know, something similar to integration.
Okay. You're just going to give me some numbers. So give me a number.
Like the integration of 5 to 6.
5 to 6
About 3dx.
of what?
3dx.
3dx. How do you do that? Is that what you're asking? Okay, here's what I would do. I'd pull the 3 on the outside, have 3 times the integral from 5 to 6 of dx. Or it's the antiderivative of dx, or 1 dx. Did someone say x? Yeah. It'd be 3 times x evaluated from 5 to 6. Right? Antiderivative of 1 is x, because the derivative of x is 1, right? So the antiderivative of 1 is x. So the antiderivative of dx is x. Remember, if we did a substitution, she said, let u equal x, then dx would be, du would be dx. So the antiderivative of dx is x. Is that what you're asking?
Yeah, that's what I'm asking.
Yeah. And then how would you evaluate that? Is that what you're saying?
You just have to go both of them. You do 3 times 6 and 5 times 2.
Okay. It's 3 times, parentheses, 6 minus 5. 6 minus 5 is 1 times 3 is 3. Right? Well, I'm not sure we actually stopped. Let me just see. This was in section. Let me see which section that was. Yeah, this is area. Okay. Example 3 on page 274 be one sort of like that. Number 48 at the top of page 279 is not the same. Ooh, goodness gracious. It is the same problem. I didn't know they ever did that.
Well, the problem for the book is on the test.
Yeah, I think so, isn't it? It sure looks the same to me. It's just that they drew the picture for you here, and I gave the equation for you on the other one. Oh, the question's different, okay? They're asking for integral from 0 to 1 of minus f of x dx and integral, yeah. They're asking different questions. The one we had is just from 1 to 11, 0 to 11. Okay. But that's exactly the same graph that I just did here. It's just asking a different question. Their question was these little ones, 6 little questions down there, whereas the one the test asked for was what's the total integral from 0 to 11. But that's the same figure as this one. All right. Any other questions? That it? Yay or nay? Any others?
Number 10 was confusing, but we need to get started.
I can't hear you say again.
I said number 10 was confusing, but we need to get started with class. Number 10 on the test.
Number 10?
But we need to get started with class. Can we do that for the other time? I mean, it's pretty much similar to what we just said a couple minutes ago, just using square root. So we should be able to do that, right?
Okay. You're asking about number 10.
Yes.
Okay, and what about number 10?
I was saying, isn't it similar to number 9? We just gotta make sure we have to get rid of the square root first by undoing it or pivoting it to negative 1. Or
Still not quite understanding the question.
so number 10,
Right.
to undo is similar to like number 9, but you have to
Yeah.
undo the square root. So you take it out of the denominator with the can't remember the term. I know you're supposed to use a negative 1 in the exponent to represent the square root.
No, you wouldn't use a negative 1 to represent a square root. What do you use to represent a square root? As an exponent.
And the exponent.
Square root is anybody.
Or 1/10.
1/2.
1/2.
Yeah.
I'll just do something else. So what was the name?
And since it's in the denominator, that's going to be an exponent of negative 1. Okay? Right. Does that answer it? Okay. What would be your innermost part that you would use as your u?
45.
Yeah, exactly. 4t plus 5. Exactly. Go from there.
Yeah.
Okay? Does that answer it? All right. Any others? All right. Sorry I got that to you so late. I wish I'd have gone and gotten it to you when I first did it. Okay. I had the test made up all this time. I thought we're just going to do a few things in chapter 5. The more we were in there, the more, yuck, look at all this mess. Okay. So, no more questions on the test. Did you get a copy of the test? Okay. Everybody did. Okay. All right. I think this is where we are. evaluate this limit. The limit as x approaches infinity of 1 plus 1 over x to the x power. Okay. Now, if you think about this too hard, you might get a headache. Okay? This is 1 plus 1 over x. As x goes to infinity, 1 over x is going to 0. Right? So you would have, if you did that part first, that'd be 1 to the infinity is just 1. Yeah, bank on it being that easy. Okay? But if you did this, forget about this, and raising anything greater than 1 to infinity, that's blowing up. So it's going to be something between 1 and blow up, right? We just don't know what. Possibly. It may be blow up, or it may be 1. Or it can be something in between. So how are we going to do that? Okay? Here's one thing they suggest, and this, whenever you have these powers like this is usually a good idea to do. Let's let, it's kind of like a substitution, let's let y be this thing we're looking for. Y equal 1 plus 1 over x to the x power. Okay? Now, that doesn't make it any easier. But what does make it easier if you take the log of both sides. Now we have log y is equal to what? Using the rules of logarithms. What would log y be? These are properties of logarithm. Okay. Okay.
Page 366.
What's that?
I was saying the page 366, I believe.
I think it's 5.3, maybe. Maybe not. 5.2. Natural logarithm, there it is. It may not even be in here, but maybe it's just counting on you knowing this from before, from an earlier life. Oh wait, I didn't go far enough back. Is it 5.1? Yes. So it is exactly. 5.1 on page 316. Number 3 there.
Oh, yeah, that's right.
What's that?
It would be x and then log of 1 plus 1 over x.
Right? Right. That's it exactly. Now, you're letting x go to infinity, right? So let's do this. Log y is equal to x times the limit as x goes to infinity of 1 plus 1 over x. All right. Well, that would obviously be 1. So now we've got a form which is of the form of infinity. That's an ugly, ugly infinity, isn't it? Okay. Okay, that's a little bit better. Infinity times 1. Okay? Because that would be the limit if you did that. Now, is that one that we can use L'Hopital's rule on? Well, maybe not quite. Okay? Because that wasn't one of the ones, if you turn back for L'Hopital's rule, that wasn't one. If you'll notice, if you convert it to 0 over 0 or infinity to infinity, that would be okay. Or 0 times infinity, that would be okay, but not 1 times infinity. But there is yet another way you can write this. Okay? Now this is going to do a little bit of shell game. Is x the same as 1 over x? Yes, it is. So this would be the same as the limit of 1 plus 1 over x over 1 over x. And this would be as x goes to infinity. Okay? Now, I left off my log here. Okay, sorry. I was going to say, this isn't panning out right. I left off my log there too. Now it's better, because what is this? This is 1. Log of 1 is 0. So this would be an infinity times 0, but if you move this down here, this is a 0 over 0, right? So we should be able to do that using L'Hopital's rule. Okay? And what would that give us? And this, remember, is all what log y is, which we're not really interested in log y yet. We're going to come back. We're interested in what y was. Okay? But let's do log y first. So this is the limit as x goes to infinity of log of 1 plus 1 over x over 1 over x. Get out of there. Okay. Right? Now, that is a form which is 0 over 0. And that's one that L'Hopital's rule should apply to. So let's do L'Hopital's rule on that. And what would that be? Yuck. What would this be? What is the derivative? Remember L'Hopital's rule? Take the derivative of the numerator, take the derivative of the denominator. What is the derivative of that numerator? Okay, not quite. Derivative of this is 1 over 1 plus 1 over x, right? That's the derivative of a log. Is
Oh, yeah.
right. Oh, yeah, right. Okay. But then you got a chain rule, and you got to do the derivative of your what's inside that. Okay. And here's where I am real tempted to write that as 1 over, wait, I'm sorry. All right. 1 plus 1 over x, that's what we're trying to take the derivative of, right? I think it's easier. I'm not sure that it is, but I think it's easier to write this as x plus 1 over x. Isn't that the same thing? Okay. Or maybe even easier than that would be No. There's no reason to do that. What's the derivative of this? Derivative of 1 is 0, right? Derivative of 1 over x is, write that as x to the minus 1. What's the derivative of x to the minus 1? Derivative of that is x to the minus 2, but minus x to the minus 2. So that would be, quit. Okay. Minus 1 over x squared. Okay. So it's this times a minus 1 over x squared. Okay. Divided by, and what's the derivative of the denominator?
It's sort of frazzled right now. Going back from other stuff and then switching back to this.
Okay. All right. What we've taken the limit of this thing, log this over this. Okay. And if you let x go to infinity, that's going to 0. That would be 1. Log of 1 is 0 over that going to infinity would be 0. Okay. So this is 0 over 0. So what we're doing is taking the derivative of the numerator over the derivative of the denominator. The derivative of the numerator is 1 over this. 1 over this thing. That's the log part. Then the derivative of the denominator of the inner part, derivative of 1 is 0. Derivative of 1 over x is negative 1 over x squared. Right? So down here, the derivative of 1 over x is also negative 1 over x squared. Right? So this thing is going to 0. Is going to 1. Same thing. So now all we need to do is take the limit of this thing. I didn't leave enough room. Let me. The limit as x approaches infinity of that. Say again?
So it's going to 0.
Okay. This is 1 over 1 plus 1 over 0. Yeah, x going to infinity. That's going to infinity. 1 over x is going to 0. 1 plus 0 is 0 is 1. 1 over 1 is 1. So that limit is finally 1. The limit of all that is 1. So now we've got the log y is equal to 1. Now let's get back and get what y is. What would we do to that?
Multiply by e.
All right, not multiply it, raise it by e. Okay? And that would then be e of log y would be e undoes a log undoes e. Finished already?
Just on that,
Okay. All right.
E to the y.
No. Okay. No. A log undoes an e. E undoes a log. So if this is undoing the log, e's undoing the log, what are you left with?
Y.
Y. And y is equal to e. E to the first power, just e. So that is indeed what you got here. That is the definition of what e is. It's 1 plus 1 over x raised to the x power. Now, if you want to play around with this a little bit, I thought they had already done this somewhere. Let me see if I can find it. Not there. Maybe I'm wrong. I've taught this so many different. Wow, here it is. Yeah. Theorem 515, I'm reading backwards. In the previous section, 5.5, which we skipped. So that's maybe why you don't remember it. That is exactly the limit of 1 plus 1 over x to the x power is e. That's the definition of e. So this is just proving that definition. Yeah, in that little table to the left of that, it uses different x values. Okay, when x is equal to 10, evaluate that, you get 2.59. Use x equal to 100, you get 2.7048. X equal to 1,000, you get 2.71692. 10,000, 2.71815. 100,000, 2.71827. A million, 2.71828. And if you kept going up and up, you'd never get any more precise than that. So it's on page 356 of your text if you've got that. Okay. All right. That was example 5. Let's see how they do it. I think they do it very similarly because I was kind of using them as a thing. Because the direct substitution yields an indeterminate form, 1 raised to the infinity, which you would think that would be 1. It's not, okay, not necessarily. You can proceed as follows. To begin, assume that the limit exists and is equal to some value y. That's what we did, okay? That's equal to that limit. Then you can take, because the limit, what's inside the limit was going to be improved on if you take a log of it, take the log of the left-hand side, log y, and then take the log of the right-hand side, that'd be log of that limit. But again, the log of a limit is the limit of the log. So flip those around, and you have y is equal to the limit as x goes to infinity of x log 1. They skipped a step there, but log 1 plus 1 over x. Okay. Now, here's where they did what we did later. I told you, think of x as 1 over 1 over x. So it goes down here. That makes the numerator. Now when you do take this limit, you get, as x goes to infinity, that is going to, 1 over x is going to 0. 1 plus 0 is 1. Log of 1 is 0 over 0. That's an indeterminate form. And that's an indeterminate form we can use L'Hopital's rule on. So that's what we did. And the derivative of the overall function is 1 over this thing. So that gave you that. And then the derivative of this thing, derivative of 1 is 0, derivative of this is minus 1 over x squared. And that's the same as the derivative of this, which is minus 1 over x squared. So those go out, and you're left with that, and that would be the limit as x goes to infinity. That would be 1 over infinity would be going to 0. 1 plus 0 is 1, so you have 1 over 1. Okay, so that would be, yeah, the limit of that thing, because those two cancel out. Then take the limit of that, and that's simply 1. That's what I just said. Okay. Now, that's what your log y is equal to. So if log y is equal to 1, then take an exponential of both sides, and that gives you y is equal to e to the 1, which is e. And there we obtained this, which is exactly the same form as you had back in the previous section. Now, they say use a graphic utility and show this, and let x approach infinity. They only let x approach 8, and it's still awfully close to 2.7. Well, that's not really all that close, but it is getting closer to it. It's not a very good graph, okay, to give you the actual value. Okay. Now, top of the next page, 367, L'Hopital's rule can also be applied to one-sided limits. And are they going to show example 6? Yes, here they are. The limit as x approaches 0 from the right-hand side only, from the upper side. Guess what you would do here? Any guesses? Goodness gracious, my eyes are so dry.
There's a plus next to the 0, so I would just
What's that?
plug it in. I'm not sure. Because I see a 0, there's a plus next to the 0, so I'm not sure what that stands for.
All right. Okay. So you say plug it in.
That's
Okay.
my plus next to it.
All right. What you have then is sine of 0, which is 0 raised to the 0th power. And what is 0 to the 0th power? Undefined. Okay. So that's plugging in alone is not going to be good because anything to the 0th power is 1, except 0 to the 0th power is undefined. So that doesn't help us any, but it's a good first step. You always try that first. Okay? And when that doesn't give you anything that's useful, then what would you try? Very similar to the last problem. Yes, let's just assign some value to that. Did y'all like y fine, or you want something else? Just don't make it x.
That's fine.
Y, okay, so we'll y. Then take the log of both sides. That would have been the log of y is equal to the log of the limit as x approaches 0 from the positive side of sine x raised to the x. Okay? Now, do the same thing as we did before. Bring the limit on the outside. Limit as x approaches 0 from the positive side of log of sine x to the x power. And what would that be? The limit as x approaches 0 from the positive side of, help me. What's that?
Just making sure I had it all written down.
Okay. What's the limit of something raised to a power? The log of something raised to a power.
Will be infinity, wouldn't it?
Well, we don't know that yet. I'm just saying, what is the log of something raised to a power?
You have to put the x out in front.
It would be the power. Yeah, put the x in front times the log of sine x. Okay. Now, what kind of form do we have here then? As x is going to 0 from the positive side, this is 0, and the log of 0, the sine is 0, and the log of 0 is infinitely small. So here you have 0 times the negative infinity. That's not very good either, okay? So again, if we can write this as same type thing as before, x is the same as 1 over x, right? So this would be the limit as x approaches 0 from the positive side of log sine x over 1 over x, okay? No, 1 over x, not, because the x is up there, and that would be 1 over x, so this is just 1 over x, sorry. I got too many 1 overs in there. Okay, there we go. All right. Now what do we have? This is a log of 0 a bit bizarre, isn't it? Okay? It's basically an infinity over infinity, right?
Would it be a negative?
Yeah, well, it's hard to say. Okay? Now, it's an indeterminate form, negative infinity over infinity. So what do we use on something like that? L'Hopital's rule, okay, that'd be the limit as x goes to 0 from the positive side of, what is the derivative of log of sine x? You can do it. So, yeah, that's what we're doing, L'Hopital's rule. What is the derivative of log of sine x? First part of it would be, what's the derivative of any log? No.
1 over.
1 over. So that would be 1 over sine x, right? Times the derivative of sine x. And what's the derivative of sine x?
Cosine.
Okay? So that would be cosine. X over sine x. That's the derivative of the numerator. And what's the denominator? Derivative of that. We just did it.
X squared.
1 over x squared. Negative 1 over x squared. Because you'd write that as x to the minus 1. Derivative of that would be minus.
That's cotangent right there, isn't it?
That's cotangent in the numerator. And so let's do that. The limit as x approaches 0 from the positive side of cotangent x over minus 1 over x squared. So, as x approaches 0 from the positive side, what is cotangent x? Because, again, it's cosine over sine. Cosine of 0 is 1. The sine of 0 is infinity, so that would be a positive infinity. Over, as x goes to 0, this is going to 0. So you have an infinity over 0. The negative side. Is that right? Yeah. No, I'm sorry. That's infinity. 1 over 0 is infinity, but it's from the negative side. So again, we have a negative infinity over negative, a positive infinity over negative infinity, which would be whatever that would be. So do you want to try it again? Okay? Seems like a pain in the neck, but let's try it. Do you remember what the derivative of cotangent x is?
Could we go back to cosine over sine and take it earlier then?
Okay. Derivative of cotangent x, if you look at the front of your book, inside cover, derivative of cotangent x is minus cosecant squared x, which just seems to be getting worse and worse. But let's try it. That would be the limit as x approaches 0 from the positive side of minus cosecant x, so cosecant squared x, and derivative of minus x to the minus 2 would be x to the minus 3, so it's 1 over x3. All right, now, does anyone remember what cosecant x is? Okay, if you think about your secant function, it's like this. The cosecant function I think in terms of the graphs, okay? Sine goes like this, right? So cosecant is 1 over sine, so it's going to have a vertical asymptote there everywhere sine is 0, okay? And cosecant would be like this. So again, you're going to positive infinity, except that it's the minus cosecant, so that would be going to negative infinity. So this would be a negative infinity over, when x is going to 0, that's over a positive infinity. Okay?
Is that better?
What's that?
I was asking, is it better?
I can't say again.
Is that better because we get the negative out of the denominator? So it'd be a negative infinity over a positive infinity instead of a positive infinity over a negative infinity, but still.
No better, no worse, okay? Same type thing, okay? Now, perhaps a better way to look at this would then be, rather than taking that derivative, let's go back and say 1 over cosecant is sine. So this would be the limit as x approaches 0 from the positive side. This would be a sine squared in the denominator, because cosecant is 1 over sine, okay? And we're going to have a minus out front, and 1 over 1, so this will be an x cubed over sine squared with a minus sign out front. So rather than doing this, that's a little on the crazy side. Let's do it like this. Those are easier to evaluate. What do we have? 0 over 0 again, which is still, well, only now it's a minus, is still an indeterminate. Let's do L'Hopital's rule one more time. That'd be the limit as x approaches 0 from the positive side. And what's the derivative of that? Let me put the minus up front. Derivative.
To the fourth over 4.
No, derivative.
Oh, 3x.
3x squared, okay, over, and what's the derivative of sine? Sine squared is 2 times sine x cosine x, okay? And the limit as that goes to 0 would be 0 over 0. My word, will this never end? Wait. Actually, I went too far. Yeah.
Where did you go too far at?
Yeah. Let me back up. Log of sine is cotangent over, this one right down here, okay? Sorry, I went too far. Let me go back here. Yeah, my eraser's not working. Okay. Let's go back to this one. All right. Sorry. We got it right, but I took it one step too far. Okay. This limit, as x approaches 0 from the positive side, this would give you cotangent x. You remember we did this over minus 1 over x squared, right? This is the one we need to change. I'm sorry, I took you in the wrong direction by going here, okay? Let's change this to be the limit as x approaches 0 from the positive side of cotangent is 1 over tangent. So let's put tangent x there, and this would be x, a minus x squared, when you flip that over and put it back in the numerator. This is the one we do the L'Hopital's rule one more time. The limit, because this is still infinity over infinity. No.
Tangent would be negative infinity.
That's, no. It's 0 over 0, sorry. 0 squared is 0 and tangent of 0 is 0. I'm sorry, I was doing infinities. Okay, so it's still 0 over 0. So now let's take one more time. I knew I was doing too many times before. of this. What is that? Derivative of minus x squared.
Minus 2x.
2x. Okay, minus 2x over the derivative of tangent secant squared. Right? Now, this one we can do. The limit as that goes to 0 is 0, right? The limit is this secant squared. Now, again, think of secant is 1 over cosine. So cosine, the limit of that as you go to 0 is 1. So that's going to be a 1. So we've got minus 0 over 1, which is 0. Finally, that limit is 0. So who wins that battle? The 0 inside wins. 0 to any power is 0. Whew. I don't see the purpose of this at all, but they did it. Okay. Now, is that always true? Oh, wait, sorry. But remember, that's log y, okay? So log y is equal to 0, so what would y be? Take the exponential of both sides, and you get y is equal to 1. So no, that limit is 1, okay? And sure enough, at least that form of 0 raised to the 0th power is 1. Normally we say not defined, but that limit happens to be 1. And again, this is such a pain in the neck to do that to you. That is just almost excruciating. It was excruciating. How many L'Hopital's rules did we use there? Not counting the ones before. They only showed 2. I thought we did one more than that, but anyway. Yeah. Now, how are we doing on time? Oh, we still got some time. Okay.
That's 12 minutes.
Huh?
Also, we use 12 minutes.
12 minutes? Yeah. Okay. All right. They do show example 6. So let's erase all my scratch and all the bad scratches that we had in between. And let's do this. Okay, because direct substitution produces 0 to the 0th power, which we don't know, you can proceed as shown below. To begin with, assume that the limit exists and is equal to y. Now, that's a big assumption. It may not exist, but let's try it. Okay, so y is equal to that thing there. Then take a log y. Same way as we did before. And that would be, log y would be the log of that limit. And then just like before, we reverse the logs and the limits, and that log y would be the limit as x approaches 0 on the positive side of log of sine x over x, okay, because of continuity. Then we can do our log rules, that'd be x times the log of sine x, just like we did before. And that's still an indeterminate form. It'd be 0 on the left-hand side and log of 0 on the right, and that would be a minus infinity. So that's not determinable. So we put the 1 over, the x would be a 1 over x, and do that. That's now an indeterminate form, but that's the infinity over infinity, which does allow us to do a L'Hopital's rule. So let's do L'Hopital's rule on that. And that would be the log of sine x. They skip some steps there, but that does give us cotangent x over minus 1 over x squared. Okay? Well, what is cotangent x? When it's going to, x is going to 0, that's going to positive infinity. But 1 over 0 squared, negative 1 over 0 squared, is going to negative infinity. So that still is not usable, okay? But let's flip them, and cotangent is 1 over tangent. So when you flip it, move it 1 over downstairs, and that becomes tangent. And 1 over negative 1 over x squared, when you flip that, it becomes a negative x squared. Okay? Now that form is still indeterminate. 0 over 0. L'Hopital's rule again. And that gives you a minus 2x over the limit as x approaches infinity, 0 from the positive side, of secant squared x. Okay? Now, if you put a 0 in for x there, your numerator becomes 0, your denominator becomes 1. So that does have a limit of 0. Okay? But remember what this is. This is log y is equal to 0. They left that back on the previous slide. Oh, there it is. Log y is equal to that limit. So it's log y is equal to all that, which is 0. Now, because log y is 0, you conclude that y would be e to the 0. In other words, take an exponential of both sides. So that's equal to 1. Okay? So it follows that the limit, since y is equal to 1, the limit as this thing would be 1, which you would find to be a bit bizarre, I think. But anything to the 0th power is 1, except 0 to the 0th power. This form of 0 to the 0th power is 1. Okay? And here's example 7. Do we have time for it?
8 minutes.
3 minutes?
8.
8 minutes. Oh, yeah. Let's give it a shot. All right. So this is the limit as x approaches 1 from the positive side. What is log 1?
240.
Second?
Oh, no, it's 0.
0. So you have a 1 over 0 minus 1 over 0. Yeah, that's a 0 minus, no, infinity minus infinity. That's not very good. So what would you do first? Well, my gut inclination was get this over least common denominator, which may not be a good idea. That would give us a x minus 1 minus log x over log x times x minus 1. However you want to write that. And frankly, that's pretty messy. As x approaches 1, now you have 0 over 0. That, I think, is a more usable form. Yes, it is. Okay? And what's the limit of that as x approaches 1 from the positive side? Well, this one, L'Hopital's rule, I think, works quite nicely on. Let's see if it does. That'd be the limit as x approaches 1 from the positive side. And what's the derivative of the numerator? Derivative of x is? Derivative of 1 is 0. And derivative of log x would be 1 over x. Okay? There we have that. And in the denominator, we have a product rule. And what would that be? You tell me. How do you do the derivative of that product? Second? Okay, 1 over x times x minus 1. That's the root of the first times the second.
Plus log x
Log x
times 1.
times 1. Okay? Now, let's do a limit of that. Be 1 minus 1 is 0 in the numerator. And in your denominator, you have a 1 times 0 is 0 plus log 1 is 0. 0 over 0 again. Okay? Well, again, I think we can improve on this a little bit by calling this x minus 1 over x over x minus 1 plus x log x over x. Yeah. Okay. And again, as x goes to 1, that would be 0 over 1 over 0. So 0 over 0 again. Now this is not looking that much better, is it? Okay. Now let's see what happens if we take the derivative again. And this all should have the limit in front of it. Limit as x approaches 1. So let's take the derivative one more time. Okay. I think I'll go back to this form. I thought that other form would be better. It's not. So the derivative of 1 is 0, and derivative of minus 1 over x squared. We've done that a time or two, and this would be 1 over x squared, right? Be x to the minus 1, minus x to the minus 1, derivative of that would be minus 1 times minus 1 is positive 1 times x to the minus 2. So that's 1 over x squared. I keep forgetting to write my limit in front. Okay. Oh man, that denominator. Yuck. Let's write this as 1 minus 1 over x plus log x. That's the way I think I would write it. Derivative of that would be plus 1 over x squared plus 1 over x. Okay. Now, what I think I'm going to do here is multiply numerator and denominator by x squared. Do you see how we got that? Okay. So, multiply numerator and denominator by x squared. That will produce a 1 in the numerator, and in the denominator you get a 1 plus 1 over x. And as x goes to 1 there, this is going to 1 over 2. Goodness gracious! Because this is the limit again as x goes to 1 from the positive side. Yes! That gives you 1/2. Oh my word. This book is just hung up on doing these weird L'Hopital rules. I'll try to avoid those on the test if I can, because they just take way too long. But let's see. Let's erase what I got, or do you need it a little bit longer? Huh?
I think I got it.
Okay. So let's erase this. Y'all are wanting to get out of here. I can tell what y'all are wanting to do. Let's just show what they got. Because direct substitution yields indeterminate form, what we do is rewrite it like this. And that's exactly what we did, put it over least common denominators. And when you do that and take derivatives of each of those, you get 1 minus, okay, that. And when you try to do that limit, oh, yeah, we did that too. We got it over least common denominator, numerator and denominator, and got rid of 1. It's still a indeterminate form, 0 over 0. So we take L'Hopital's rule one more time, and you get 1 over that, and you get 1/2. They came up with the same thing we did, okay? And they showed a table. They like to then do the little tables. I usually don't. So here are the various forms of L'Hopital's rule. 0 is 0, infinity over infinity, infinity minus infinity, 0 times infinity, 0 to the 0th, 1 to the infinity, and infinity to the 0th. They have all been defined as indeterminate, but what you can usually do is rearrange these differences and powers in those, the last several of those, to either 0 over 0 or infinity over infinity. There are similar forms you recognize as determinate. Infinity plus infinity has got to be infinity. Minus infinity minus infinity has got to be negative infinity. 0 to the infinity, it better be 1. It better be 0. So they no, they didn't put that up there. And 0 to the minus infinity, meaning 1 over 0 is going to infinity. So basically, 3 of those have no limits, okay? So I don't know why they put infinity there. They have no limits. They, the 1, 0 to the infinity is 0. That does have a limit. Goodness gracious, one final comment. We are out of time, aren't we?
Yes.
Okay. We'll do the one final comment next time. We should have done the last 2 slides. I thought I only had 1 slide left.